flow, this is also a flow. And you know that there is a relationship and that is provided by the gear reduction ratio. I'm sorry. So that is provided by the gear reduction ratio, which acts as the transformer modulus here. And on the lead screw side, you have the moment of inertia of the lead screw, and the rotary motion of the lead screw is translated into the translational moment or the linear moment of the nut or this post, tool post, and that has been performed, that has been done using this transformer element. So you have pitch upon 2 pi coming in as the transformer modulus, and on the output side, on the mechanical side, translational side, you have the mass of the tool post and also the friction of the slide, because there would be opposition to this. So you can see that one end of the slide, one end of this would be moving against a fixed surface. Okay, so the relative motion is going to be x dot itself, and so you can assign this R or the frictional resistance for this slide over here. So this is a simple model for a simple machine tool. Here you can see that there are two derivative causalities taking place. What the derivative causality tells us in this case is that the states associated with these two elements, the rotor inertia and the lead screw inertia, in this case, they are dependent. That means the momentum, the angular momentum on account of this rotary inertia and the angular momentum on account of this lead screw are depending on other variables now in this model. Okay, and you can conveniently place them, you can transfer this inertia to other parts of this system. I am not showing you in this because that will I need to cover more examples, but it's a little elaborate affair, but one can take care of this derivative causalities by introducing some kind of viscoelastic elements. Okay, so you can take care of this just like we did in the case of the lever problem. The same thing can be done here, and actually that is a natural introduction of some natural dynamics into the system which may be needed actually. But since we are just interested in knowing how the system is to be modeled, it doesn't matter right now. Let's take into account the derivative causalities and let's proceed further. So this is another example. Here we have an example of a cam follower mechanism, and in textile machinery also you have a lot of cams which come into picture. And here you have a very simple example. You can see that there is a cam here and there is a profile for this cam, and this cam profile one can just perhaps show it here like this. So if you are to go along the angle of the cam theta, here you have, should I use the board? Should I use the board? I think it may be better.
आप यहाँ भी कर सकते हो ना, यहाँ लिखिए
Actually, the thing is the diagram will go. Yeah, no, it's okay.
What do you study the circle light? That's all.
So we have the cam profile, and over here we have the angle. So this angle can go from 0 to say 2 pi, which is the complete revolution of the cam, and here you have r, which is actually the distance of the distance of the profile. Suppose if this is the profile of the cam and you are measuring it like this. So if you consider any point here at a distance r, and this r is a function of theta. Okay, so this is a function of theta, and if you plot it here, you may get some kind of curve here. I am not exactly now this profile, it is fixed for a particular cam, it is fixed. So as this profile, as you proceed along theta, that means as this cam turns, there will be a different value for r, and of course depending upon the angle, there will be the follower motion. But right now I am just expecting that the motion of the follower is just following the radial position from the center of the cam. Hello. So we can say that r is equal to a function of theta, and the motion of the follower, it is actually dependent, one end of the follower for the benefit of simplicity, I will take this as a knife-edged follower, okay, so that it's directly in contact with the cam, and
Just tell me. भाई बोलेगा आपने सब्जेक्ट पता नहीं है, मेरे को कैसे आगे सब्जेक्ट पढ़ना।
So as this cam turns, let's assume that this cam has an angular motion. The rate at which it turns is theta dot. So omega of the cam is actually theta dot, and actually theta can be written, it can be related, theta dot can be related to the movement of the follower, and that can be done like this. So you have the motion of the follower, which is this velocity, okay, as it goes up or down, and this can be written in terms of the motion of it can be related to the angle, and this is actually the angular velocity of this is the angular motion of the cam. So at any location you can determine the slope of this curve, which is given over here, Okay, so it is something which is changing with the angle. It depends on the profile. So you can relate, you can have a transformer modulus, which is now getting modulated transformer.
सर एंगल मतलब जो कॉन्टैक्ट में जो
And
एंगल का जो भी टर्म है
you are relating on this side, you have theta dot, which is the flow. You see that this is a flow. So this is r dot, which is equal to dr by dt, and this becomes and as the cam turns, you can have a unique location. So corresponding to every angle there is a value for this. Okay, so that is determined by the cam profile, and you can straight away obtain the angular motion of the follower, the translational motion of the follower. So let us continue with our example. Yeah. Now over here we have a source which is actually driving the cam. So it is turning the cam with a predefined angular speed, and we represent that with the help of this SF, and we place it on this one junction. And let's also assign the inertia of the cam over here. So we connect the inertia of this cam here, and the motion of the follower, which is in this direction, we show it as a rate of change of I have taken this point as B, it's on the follower, and it's the velocity of the follower at descent, and we have related the profile of the cam through this transformer. So it is actually a modulated transformer, and then we have got the mass of the follower. So the mass of the follower also is modeled here. Now on this side we have the frame, the housing, and that is fixed. So we take a one junction and connect a source of flow which is 0 in order to fix the housing. So when you apply a source of flow equal to 0, it means you are arresting the motion of the housing. So XA dot, this point here, is at 0 velocity. And then there is a spring here which actually constantly ensures that this follower is pressed on the cam. So that spring has to be modeled, and the relative motion across the ends of the spring, one end is the velocity at B and the other end is the velocity at A. And so you need to take the difference of the velocities that has been taken using this 0 junction. So you have the velocity over here as equal to velocity of A, velocity of B minus velocity of A is the relative motion. And here you assign the C element, modeling the stiffness of this spring. You may also have resistance, friction between this follower and the sleeve through which it slides. So that has been taken care of using this R element. Here also you require the same relative motion. And what we have done is